Okay, let's get started. Welcome everyone. Today is our great pleasure to welcome Professor Ching Li from Wisconsin Madison to give us a talk. Uh, Let me say a few words about Professor Li. So Professor Li is now an associate professor at the Wisconsin Madison Department of Mathematics. She also holds an affiliation with the Wisconsin Institute for Discovery and is also a senior PI of the Institute of the Foundations of Data Science. Her research focus majorly on kinetic theory and more generally numerical analysis and also scientific computing. So Professor Lee's actually received numerous recognition, including NSF Career Award and more recently Simon's Fellow. So today, Professor Lee is gonna give us a nice talk about the multi-scale inverse problem from Schrodinger to Newton to Boltzmann. Xing, please.
Thank you very much. Right. Thank you for the very nice introduction. I just realized that when you asked for the bio, I forgot to give you. Okay, so it's really my great pleasure to give a talk here. Especially, I'm going to talk about inverse problem, and RPI really is an institute that stands very solidly, has a very big group, has a very influential impact on inverse problem. So let's get started. I should start with the following. So for inverse problem, I was really an outsider. I got into the inverse problem about 5 years ago. And along the way, I got help from many friends. So Ru Yulai was a student of Gunther Woman, and they are really my guiding person into the inverse problem this community. And Li Wang is my longtime collaborator. Shi Chen and Zhi Yan, they were my student. Zhi Yan is currently at Berkeley as a postdoc. And Leonardo is my new colleague, and he's really the expert on the wave inversion side. Okay, so what do I mean by multi-scale inverse problem? In my initial title, my subtitle is from Schrodinger to Newton to Euler. I think it's Euler or Navier-Stokes, I forgot. But Boltzmann. Okay, from Boltzmann. So what I really wanted to say, that putting those names over there is really to attract attention. So what I really wanted to say is that inverse problem get presented at different scales. And at different scales, we have different modeling tools. Sometimes it's Schrodinger equation, sometimes it's Newton equation, sometimes it's Boltzmann equation. So all these equations in the inverse perspective, they have some interconnections. And I would like to discuss their connections. Okay, so let's get started. Inverse problem. I know that there are a lot of experts in the community, in the audience, but nevertheless, let's still go through some basics. What do I mean by physics-based inverse problem? So over here, you have this object, and this object has a media that is unknown. So what I can do is to send some signals into this media, and on the other side of the lake, I can collect some information goes out. So I put some input sources, I call it Xi, and PDE is my machine that transfer my input Xi to the output Yi. This PDE is parameterized by the parameter theta. What I want to do is utilizing xy as my data pair to reconstruct the parameter in your PDE. So the forward problem is you gave me this PDE and you crank machine to compute for the y, and the inverse problem is to use xy data pair to reconstruct the theta parameter in your PDE. Okay. So inverse problems are really ubiquitous. So this picture is taken about a 20 minutes drive from Madison. It's in a city called Johnswell. Oh, actually not Johnswell, Huntsville. Okay, so what they do is they send the laser light into the sky and count how many kinds of time for the laser beam to come back to the Earth. And by counting this time, they can infer how high these clouds are. So as you can see, from the 0 o'clock to 3 o'clock in the afternoon, the clouds are getting closer and closer to us. So this is really the inference problem. And if you take an intersection over here, this is the scattering coefficient and the absorption coefficient. So if we translate or form this problem using the mathematical language, we are really inferring some coefficient over here. So this is my radiative transfer equation. That is the equation used to simulate the light propagation. So the light goes up and the light comes down, and over here you have some optical objects that you want to infer. So f is a distribution function, and this tells you that photon particles goes up, and this tells you photon particles, when they encounter some object, they get sent back home. So this is the parameter over here that you want to reconstruct. And the second picture, this is the equipment that was quite useful at the beginning of the pandemic. It is used to detect your oxygen level in your blood. So at the tippy top over here, that's a laser light to send the laser to your skin. And by collecting the laser information or reflection back to the equipment, they can infer for your optical properties in your finger. And using that information, they can tell how much of the oxygen is in your blood. And the third picture is collected from Austin Minnick. He's a professor from Caltech. So he is a material scientist. What he does is he would like to understand the heat conductance of a material. So over here, he put alumini right next to silicon, and he sends some wave information in. And then he detects by how much this alumini would get heated up. And using this incoming wave information and the temperature increase measured at the outside of this alumina, he's trying to infer the heat conductance at the interface of aluminum and silicon. So that's also a very typical inverse problem. So there are many more. We probably should not go through every single one of them. But at the end of the day, what I wanted to say is that inverse problem is everywhere, and all of them can be formulated and minimizing some mismatch function so that my underlying forward PDE solvers is accurate. Okay, so let's get down to the problems that we want to talk about. Now I want to present you 3 particular inverse problems that are heavily studied in the community individually. So the first inverse problem is seismic tomography, and the mathematical name for it is inverse scattering. So underlying partial differential equation is a Helmholtz equation, which is really the wave equation presented on the frequencies domain. The data that you can collect is the incoming wave information and the collected wave information. So you send some wave in and you collect some wave out, and using this incoming to the outgoing wave information, you are trying to reconstruct the refractive index underneath the ground. Hopefully you can guess. So that's a very typical inverse problem that has been very well studied, and a lot of the older results are really from RPI. So I really should I pay a lot of respect to the RPI community. Okay, so the second inverse problem is called optical tomography, and the mathematical version for it is the inverse radiative transfer equation. So the underlying PDE or the forward model is a radiative transfer equation. This unknown parameter theta is the optical property. Usually it's either the absorption coefficient or the scattering coefficient in your human body. The data that you can collect is you send some light onto the skin, and you collect the light goes out of the skin, and you use the incoming to the outgoing light sources to reconstruct the optical property in your human body. The mathematical term for this incoming to the outgoing light information is called the albedo operator. Okay. The third inverse problem that has been heavily studied in the community is called electrical impedance tomography, and the mathematical term for it is the Calderon problem, pinned down by Calderon in 1960s. So the underlying differential equation is the easiest equation that you take in the PDE course. It's an elliptic type equation. And in the elliptic type equation, there's a term, it's basically the diffusion coefficient. in reality is called the electrical permeability coefficient that is not known. So you want to infer this. And what you can do is you prescribe the Dirichlet boundary condition for the elliptic equation. And in science, we say that we put down the potential on your human body and we detect for the flux. The flux, the mathematical term, is the Norman boundary condition. So we use the Dirichlet data to Norman data as your data pair to infer for the diffusion coefficient in the elliptic equation. Okay, so let's put down a 3 inverse problem side by side. The inverse scattering is the inverse Helmholtz equation. The optical tomography is the inverse radiative transfer equation. The Calderon problem is the inverse elliptic equation. So these 3 equations are written down over here with associated 3 different data pairs. Okay, so all these 3 problems are heavily studied, and there are a lot of results on the well-posedness of the 3 problems. They look very different from on paper. What I want to claim, what I'm going to claim right now is a pretty big claim, but we're going to get there. I'm going to claim that these 3 problems are the same problem, merely presented at different scales. So before doing that, I realized that our seminar is an optimization seminar, so I need to draw some relation with optimization. So as you can imagine, all this inverse problem, when you numerically need to execute it, usually it's formulated as the PDE constraint optimization. So you have this PDE equals on the PDE operator acting on the solution equals to the source term on the right-hand side, and you hope the measurement of your solution would agree with the data as much as possible. So we're looking for the optimal configuration of the parameter in your PDE so that the simulated data agree with your real data. So your loss function is in this summation form. So very naturally, the stochastic gradient descent would be a very good algorithm framework to fit for this particular setting. I should also say that although we call it the PDE constraint optimization, but PDE, when we write it down, is usually well posed in the sense that you can invert this PDE operator for the solution. So if you do that, you invert this U, insert this solution U to the objective, that's really change it into the non-constrained optimization. One more word. If you want to find the minimizer for this PDE constraint optimization, there are millions of algorithms out over there. But at the end of the day, all this algorithm needs to discuss the conditioning of the objective function. What I'm going to say today, later on, is that the conditioning for some of the problem presented here is very bad, but the conditioning for some other problems are very good. Mathematically, however, all these problems are asymptotically equivalent, and we are going to discuss what does equivalent mean later on. So there are some ambiguities on why all these problems are equivalent, but some problems are yield conditioned and some of the problems are under the better condition. So there must be some way to manipulate or massage this problem to formulate a good problem. Okay, so let's move on. Yes.
Can I have a quick clarification of your notation? So I assume the SI and the DIJ is sort of the given training data. Right, SI is just.
Oh, right. So SI is the input of the machine, and MJ is the detector. So they together is the simulated data.
Okay.
Right. Then you're comparing the simulated data with the true data. Right.
Okay. The L depends on theta. Right.
Right. L depends on theta. Yeah, you're right. Thank you. Yes. Yeah. Okay. So let's move on to the multiscale part. As what I tried to claim earlier is that inverse scattering for Helmholtz equation optical tomography for the radiative transfer equation and EIT problem for the diffusion equation, they are the same inverse problem presented at different scale. What do I mean by that? So if we think about multi-scale structure, let's think about the physics in general. So the physics presented at the nanoscale, we say it's a quantum regime, and in the quantum regime, the governing equation is a Schrodinger equation. And then you gradually enlarge the scale at the mu m level. We say that all these particles, they follow the Newton's second law. We are in the classical mechanics regime. And then you enlarge the scale a little bit more, you have a whole bunch of particles all together. Then we have the statistical mechanics, and the fundamental model over there is a Boltzmann-like equation. And finally, as a meter scale, we have the fluid dynamics. In the fluid dynamics, we have the Euler-Navier-Stokes equation. So if you change from one regime to a different regime, the governing equation changes. However, this happens to pretty much all kinds of particles. For electrons, at the quantum regime, we have Schrodinger. At classical regime, we have Newton. At statistical, we have Boltzmann, etc. And for photons, for the light propagation, the story is the same. The classical regime, you have the Maxwell equation for the magnetic wave equation. And in the statistical level, you have the radiative transfer equation. And finally, when we think about the light in our room, for example, everywhere the light intensity is pretty much the same. So you're really experiencing a diffusion effect. So that's a diffusion equation. So photons, or the light propagation, can be described at different levels by different sets of equations. So this kind of phenomena made some people mad and some people happy. It made physicists really happy. For example, Einstein, I don't know if happy, but let's say it's happy. Einstein says that basically draw the conclusion of the wave-particle duality. He was saying that light cannot be purely described as wave, and cannot be purely described by particles. Only by collecting them, you can understand light propagation. So it's a very new phenomenon. On the other hand, mathematicians get really bothered by this fact. And Hilbert proposed to study this problem as his number 6 problem. He was saying that the physical phenomena is just light propagation. How come one particular description, one particular physics get described by all different kind of equations? So all these equations should be somewhat connected. So we pretty much spend the whole century studying this Hilbert 6 problem. And to today, we roughly know that the underlying structure that connect one equation to the next hides underneath the asymptotic analysis in the following sense. So suppose we're looking at the Schrodinger equation. There's a Planck constant called h bar. And we usually say h bar is negative 34 and tiny. So h bar is a very small number. But if you really think about this h bar equals to 10 to minus 34, it comes with a unit. And this unit is like meters and second and a kilogram, all this kind of unit. These are the units that we human beings use to sense the world. We count the time by second, and we lift the heavy stuff by kilogram. But this is not the unit sensed by electrons. Electrons are tiny. They sense the world using the nanoscale. So if you rescale everything in the nanoscale to represent this h bar is not such a small number anymore. But nevertheless, let's suppose that we want to view the electron dynamics using our scale. Then h bar is a very small number. And with this h bar being a very small number, you can mathematically derive the Newton's second law directly from the Schrodinger equation. So we are basically saying when h bar is very small, these two equations are asymptotically equivalent in the sense that Schrodinger equation completely recovers Newton's equation. The same story happens from Newton's equation covers the Boltzmann equation, and the Boltzmann equation recovers the Euler-Navier-Stokes equation. And all these derivations are summarized in a lot of references that I list over here. There are way more. I'm just listing the ones that I can understand. So the underlying mathematics is really very similar, whichever regime you are in. The mathematics is pretty much the same. It's asymptotic analysis. So you have a PDE operator, and this PDE operator has a very small parameter, epsilon. And by sending this epsilon goes to 0, you are saying that your solution can be asymptotically expanded in terms of epsilon as well. So you put this asymptotic expansion back into this equation and conduct layer by layer agreement, you will find at the leading order, this equation becomes the next equation, this L star equation, and this L star equation completely eliminates the small parameter. So that's how we derive the Newton's second law from Schrodinger and how we derive the Euler equation from Boltzmann. Okay, so with that said, let's come back to the photons for the light propagation. For photons or the light propagation, we can think of light as Maxwell wave equation, or on the frequency domain, it's translated to the Helmholtz equation, or we can think of light as a statistical behavior radiative transfer, or we can diffuse everything out and we have the diffusion equation. So light gets prescribed into different form of the equation. The conjecture now is if I conduct the inverse Helmholtz, inverse radiative transfer, and inverse diffusion with the 3 inverse problem also asymptotically somewhat equivalent. So that's my ultimate goal. Let's go down to this diagram that we showed before. Previously, I showed you everything above the data set. Over here, I wanted to say that when we started thinking about this problem, we immediately encountered difficulties. The difficulty is the following. So you start from the inverse scattering operator. You start from the inverse Helmholtz equation. And you read into the literature, you find out that this problem is very ill-posed. So you perturb the data by a little bit. The reconstruction gets perturbed significantly. But on the other hand, the inverse radiative transfer is a well-posed problem. You perturb the data by a little bit. The perturbation gets linearly reflected in the perturbation in the reconstruction. And then you move on to the inverse elliptic equation. The inverse elliptic equation is once again logically ill-posed. So somehow, in some sense, the 3 inverse problems, we believe they are equivalent, but their associated conditioning is very, very different. So we want to understand why. So this has a significant impact on the PDE constraint optimization. In the landscape over here is pretty much to tell you how sensitive you are with respect to the data. If you are not sensitive, if you are sensitive, then you are immediately in the minimizer, so you have a very sharp objective function. But if you're insensitive, you have a very flat region, then you have a very large region that can be sort of regarded as a minimizer. So this is a very bad problem. So in reality, we basically need to think about how to design our problem that are kind of equivalently described by 2 different mathematical formulations, but something has a better conditioning in the PDE constraint optimization setting. Okay, so now let's move on to more details. The first section is radiative transfer passing down to the diffusion limit. So this is one of my favorite pictures. If you think about the light propagation, atmospheric scientists use a radiative transfer in the sense that the sun shines up the earth, some of the light propagates through and some of the light gets scattered by the cloud. So these 2 terms, one term is to say we have transport and the other term is to say that the light gets scattered around by the cloud. So the sigma over here indicate how thick your cloud is. And then we have this equation, the diffusion equation. It was sort of hinted by Da Vinci 500 years ago. He said, if you move an object 5 times away from me, this object looks 5 times bluer. So the sky is blue for good reason. So he was basically saying in the entire spectrum of light, blue light diffuses the fastest, so you can spot them. So in terms of the diffusion effect, you write down the diffusion equation. And the underlying structure really comes down to this smallness of the Nussen number. Nussen number pretty much just describe how many times a photon would scatter before it leaves out the room. Suppose you have two light sources. One is a laser light, and the other one is a flashlight. You turn on the laser light photons, they go straight line without scattering. So it's very straight. But the flashlight, the photon comes out and they scatter frequently, so you observe a diffusion phenomenon. So Nussen number going to 0, you're basically passing from the laser light to the flashlight. Mathematically, we write down the solution to the radiative transfer equation in terms of the Nussen number. There's the leading order expansion and the higher order expansion. So you plug this ansatz back into your radiative transfer equation and conduct this layer by layer matching. You find out in the Nussen number going to 0 limit, the distribution function, which is really a function on space and velocity, become a separable function, one function on space only and one function on velocity only. Moreover, the function on the velocity is a fixed function. There's nothing you can change, and the function on the spatial domain is a diffusion equation. So this pretty much explained why in the Nussen number going to 0 limit, you are passing from the laser to the flashlight, the equation changes from the radiative transfer to the diffusion. Then we move our knowledge to the inverse setting. We want to understand if we do the inverse radiative transfer versus inverse diffusion, are they equivalent as well? Sort of. So the inverse radiative transfer is the optical tomography. The picture that you see is kind of very, very sharp. And earlier we said the problem is Lipschitz stable. So the perturbation in the data gives you the linear perturbation in the reconstruction. But if you tone down your frequency of the light, instead of using very high frequency light, you use a low frequency light, the light that scatters a lot, you are in the diffusion region. And in the diffusion region, the inverse problem is the Cateron problem, which is logly opposed. So now the question is, what's going on? How come one problem is well posed when the other one is opposed? So let's go down deep to this problem. So optical tomography, I send the laser light in and I collect the laser light out. So I have this incoming to the outgoing light information for my reconstruction of the media, my hand. So this reconstruction is linearly stable. You have the perturbation in the data, let's say 1, then this 1 get magnified by a constant in your reconstruction. So this is very small. But the Cateron problem is logly opposed. You perturb this directionally to Norman map by a little bit. This omega function is a horrible function. It's something like phew. So you change your data by a little bit, the reconstruction get magnified by quite a bit. So the problem is we can show that the radiative transfer equation in the Nussen number goes to 0 limit becomes a diffusion equation, and we can also show that the data for the radiative transfer becomes the data for the diffusion. But somehow one is stable, one is unstable. And we trace the dependence of this yield conditioning to the data. So this is one example numerically. Before we had any theoretical result, we ran the test. So this test is very simple. This test is, I have a Gaussian bump over here, and the only unknown variable over here is the height of the Gaussian. So there's a reference height, and I increase the height and decrease the height, and I evaluate if I change the height of this Gaussian, do I change the data? The data basically get linearly changed if you perturb your media. However, if you have a small Nussen number, if you have a very small Nussen number, the change is very, very small. It's still linear, but you have to change your media by quite a bit for your data to observe a little bit of perturbation. So in some sense, your data is insensitive to your media reconstruction. So this is the same problem, just presented on 2D. You have two Gaussians, so two bumps. And then we traced it. We try to trace this yield conditioning, and we find out this yield conditioning is really nothing but this Lipschitz constant itself blows up as Nussen number goes to 0. And it blows up in a very bad way. If the Nussen number is small, you have e to pretty much infinity. And that basically carried you to this logarithmic yield conditioning in the diffusion limit. Okay. So we numerically try to recover or represent what we have learned. And if your media get changed, we see that the data perturbation also linearly reflected. And this linear slope is a function of the Nussen number. When your Nussen number is small, the coefficient is big. So this plot is pretty much to confirm the theories that we had before. We truly have the Lipschitz stability, but the Lipschitz stability constant blows up when you are in the diffusion region. So this is kind of a little bit of an intuition of why this is happening. If it's something not interesting to you, don't take a break. So what I'm trying to say over here is when Nussen number is relatively big versus Nussen number relatively small, what is the difference between the physics? Imagine that you have a laser light. Laser light corresponds to the situation when epsilon is relatively big. That means your laser light truly just go with a straight line, and on the other side of the domain, there's one point you can see my laser. You move to a different spot, you cannot see my laser. So this is exactly what is happening. The x-axis is the different location I put my laser in. And this y-axis is a different location I detect the intensity of the received light. So when you shoot out a laser, a very thin beam, on the other side of the lake, you can, for every source on the other side of the lake, you can only have 2 or 3 detectors that can see the information. So in some sense, you're really tracing precisely the information in your media. But if you shoot out a flashlight, for example, with your flashlight shoot out at one single location on the other side of the lake, there are many detectors that can receive the same information. So your information sort of diffused out. If your information gets diffused out, then the reconstruction is very bad. So that's very physically intuitive. So this is another experiment to confirm the same story. When Nussen number is 1, your laser is very similar to the so-called X-ray, which is the well-posed problem. But when your Nussen number is small, even if your beam is very thin, the simulation of the radiative transfer versus the simulation of X-ray, they are very different. X-ray is well-posed, and this inverse radiative transfer is ill-posed. Okay, so let's come down to the question for the optimization audience. We have a problem that changes from the well-posed problem into the ill-posed problem. And in terms of the landscape of your objective function, initially your landscape of the objective function is very sharp, but as you change to the diffusion limit, you basically lower down your landscape, and the landscape is pretty much flat. So you have a very large basin that you can regard your solution as a good approximation. So in some sense, we're losing out the conditioning of the problem. However, diffusion equation is much easier to compute than the radiative transfer equation. The radiative transfer equation, the computation is conducted on 5D. The diffusion equation, the computation is conducted on 3D. So you sort of decrease the computational cost by quite a bit. With a worsening conditioning, but better efficiency in the PDE solve, how do you balance these pros and cons to design an algorithm that sort of leverage both advantages? That's a question, probably a question for the optimization audience here. Okay, so that's one part of the story. The other part of the story is really pretty much the same. It's the inverse problem for the Helmholtz versus the inverse problem for the radiative transfer. So over here, this is the inverse, this is the wave equation. If you think about the wave, it's something that's oscillating, right? So this is my wave equation of the Helmholtz equation. And when you think about the particles, and the particles goes in and then bounce around and you get spelled out. So this is my particle equation, x dot equals to v, and v dot equals to acceleration given by the refractive index. So this beautiful theorem came out in late 1990s, really early 2000, that basically says the Helmholtz equation and the radiative transfer equation, they are the same equation in the sense that if my u solves the Helmholtz equation, I do some kind of Wegener transform, it's some kind of transform to compute a new function. This new function in the frequency goes to infinity limit, becomes a different function, and this different function solves the radiative transfer. So that is really to say that as your frequency of the wave goes to higher and higher, you're really viewing this wave information as a lot of particles. So this is a beautiful theorem in early 2000, and we wanted to see if the theorem can be carried to the inverse setting as well. So this slide is, I just want to emphasize how beautiful this theorem is. It really explains this wave-particle duality. If Einstein knows this result, I think he's going to be happy too. Anyway, so earlier I said that the inverse Helmholtz equation is a bad problem in the following sense. So you send in some wave information and you collect the scattered wave outside. So your map is the incident wave to the scattered wave information. And the reconstruction is very, very bad. So this C function is similar to the function that we studied before. It's a logarithmic function in the sense that you perturb your argument by a little bit, the reconstruction gets perturbed dramatically. So this is a ill-conditioned problem. On the other hand, the inverse Liouville or the inverse radiative transfer is a well-posed problem. You tell me the light that gets sent in and you collect the light that goes out. This light information is used to reconstruct your media, and this reconstruction is Lipschitz stable. So we wanted to ask what happened when you transform from Helmholtz to the Liouville as the frequency goes to infinity. The data structure must have changed so that your problem changes from a ill-posed to a well-posed problem. So what happened over there? So the more we thought about this, the more we get confused. Confused in the following sense. So when we think about the particles, I send a particle into the domain. I can tell you precisely where I put the particle in and in which direction I put the particles in. So in some sense, your information is a delta function in space and in velocity. So you can tell me where and how I put the particle in. But on the other hand, on the inverse scattering problem, in the inverse Helmholtz wave equation, the incident wave, you look at the literature, it's always two kinds. You either do plane wave tells you the direction of the wave is encoded in this S term, or you use spherical wave in the sense that you tell me the source of the wave generated by one point and everybody is having a spherical information around it. So you have a concentration in either the direction of this S or the location using this x0. So in some sense, comparing inverse Helmholtz and inverse radiative transfer, you're losing a lot of information. Your concentration gets totally lost. You have, over here we have concentration in direction or location, but on the other hand, we have the concentration in both direction and location. So the information get lost. Well, actually, sorry, information get richer if you pass from Helmholtz to radiative transfer. Let's forget about this page. So if we change the inverse scattering, instead of using the spherical wave or the plane wave, we have this as source term, and this as source term can both shrink the location of the input and also shrink into specify the direction the wave is coming in. Would the problem be better? The problem that we can prove is with this revised modulus of the inverse scattering problem, this revised inverse problem, where revised inverse scattering problem is a well-posed problem. So in this setting, when your K frequency goes to infinity, the data structure here becomes the data structure in the limit, and then both of them are Lipschitz stable. So now, this is a numerical representation. As you can probably see this guy, the wave gets spread out. So this is a low frequency wave, and as your wave gets higher and higher frequency, as your K increase, it really looks like a particle going with a straight line. And if your particle, the refractive index is non-trivial, then your particle gets bounced out by the refractive index. But nevertheless, the story is as you increase the frequency, the wave looks more and more like a particle. And this is the same story on this page. So the first picture is the low frequency wave. You send the wave in. On the other side of the lake, there are a whole bunch of detectors that can tell you the same information. But if you increase your wave frequency and you send the wave in, on the other side of the lake over here, there's only one detector that receives the information. So the information is precise. We use this new revised modulus to conduct the inverse scattering problem, and the reconstruction is much more beautiful. The first column is the ground truth, the second column is the revised modulus, and the third column is the original inverse scattering, which is yield post. So the last page is really to come back to this questioning. We show the well-postedness of the yield postedness on the PDE level, and in the true numerical execution, we need to translate this problem into the PDE constraint optimization. So how do we tune this landscape of the objective function to balance the numerical cost and at the same time obtain the well conditioning is a good question to pursue. So with that, I'm pretty much done. We have discussed the relation between the Helmholtz and the radiative transfer and the diffusion equation. All three equations are about light propagation, and we say, or we claim, the inverse setting, the inverse Helmholtz and inverse radiative transfer and inverse diffusion, they are asymptotically the same as well. So when we started this whole line of research, it was really the intellectual curiosity. We are bothered by the same physics presented at different scale have very drastically different meaning. Now we're sort of there already on the theoretical level. It's time to think about the numerical advantages. So this is a great timing. Thank you, Rongjie. So along the way, I got a lot of help from many different people. And I specifically want to thank this group who gave me a lot of guidance for conducting inverse problem. And thank you, Rongjie, for inviting me. And this is the list of the references. And I think I can stop here.